Hi guys. Thanks for joining us today. My name is Krittika, and I'm almost finished my PhD in computer science at the University of Cambridge, where I work on machine learning. I'm excited to share with you some of the work I did this past summer at the NASA Frontier Development Lab. I'll start with an overview of what is NASA FDL and then describe some of the work we did and kind of our next steps. So NASA Frontier Development Lab is a private-public partnership with NASA and a number of their private sponsors. So it's with NASA, the SETI Institute, and then numerous private companies, including Google, NVIDIA, and IBM, amongst many others. The idea is that it brings together researchers with different types of backgrounds, some of whom know a lot about space, and some of whom work in machine learning. And the idea is that they work together on really interesting problems related to machine learning applied to space. There's so much data that we're collecting constantly from satellites and different sorts of missions about space that it's available there, ready to be analyzed. And so there's a number of exciting projects that are being worked on through NASA FDL. One example is looking for metals on the moon, trying to predict solar flares, and the project that I'm going to talk about today, which is monitoring astronaut health while astronauts are in space. So it's an 8-week program that was held over the summer. I participated as one of the researchers. It's a team of 4 core researchers that we were. We had interdisciplinary backgrounds. Some of us worked in regenerative medicine, some in biomedical engineering, and I was and some in machine learning as well. And we had our mentor as well, I'm happy it was here as well, back in the corner, Frank, and Freddie as well, who was a mentor. So if you have questions about NASA FDL, I'm happy to discuss it, and I'm sure they are as well afterwards. So the future of space exploration is exciting. As we move from manned missions to the International Space Station, to more distant interplanetary travel, to the moon, Mars, and hopefully beyond, all of the astronauts on these missions are being exposed for longer periods of time to microgravity and radiation. So if we truly want to see humans, and not just rovers, reach deep space, we need to augment our current capabilities with AI. And we need to prioritize the health of all of the astronauts, and we need to enable their autonomy in space. So what does it mean, enabling their autonomy? The idea is that as you get further and further away from Earth, the amount of time that it takes to transmit a message back to Earth increases. Sending a message from Mars can take multiple minutes just to get back to Earth. And so if you had an astronaut on Mars, for example, that had some sort of health condition, maybe a heart attack or some other issue, you want to have resources at the ready that they can use to potentially early to monitor their health conditions, early diagnostics for issues that might come up, and then also working to treat those issues. So we hope that this project is the first step in enabling autonomous healthcare for astronauts in space. There's numerous health risks associated with space. Among others, there's cancer, vision impairment, and muscle atrophy. The heart in particular has an increased risk of muscle atrophy combined with a higher risk of cardiovascular diseases such as atrial fibrillation. One of the things that we saw when we sent astronauts to space for the course of 6 months was that they conducted an experiment in which they took scans of their body every single month for those 6 months. And it was interesting to see that over just 6 months, the muscle mass decreased by 10% of their heart. And that's significant. If you think about your mass decrease, the mass of your heart decreasing by 10%, that completely changes the blood flow to different parts of your body. You're physiologically changing these astronauts as they're in space. And the reality is we don't fully understand all these health conditions that are happening. And as we send astronauts for potentially years into space, we need to be able to understand what's happening and also treat it. So that's one of the goals of NASA as well as the Canadian Space Agency. So I truly believe that in the same way that we continuously monitor all of the engines of our spaceships, we should be continuously monitoring the health of our astronauts. So what they've done is that they've had astronauts in the International Space Station wear what's called an astroskin. And they did this for a small test experiment. And what an astroskin is that it's a wearable smart suit. So it's kind of a suit that's worn by the astronauts under their space suits, and it has a number of sensors throughout. And those sensors enable us to collect data continuously. So we have data about their skin temperature, the respiratory rate. There's also a wearable ECG, and that gives us an indication of the electrical activity of their heart. So what an ECG is that it's an electrocardiogram. So what that gives us is indication of their heartbeats and also potentially help us to diagnose if there's heart conditions that they have. Now there's pros and cons that come with wearable devices. If the astronauts were lying down in a bed and attached to a clinical ECG, we would have a much clearer signal that we would get. The flip side to that is that they would be connected with lots of different wires to this clinical ECG in a clinical setting, and it's not practical for if they're in space. And they're doing different activities, and they're walking around, and they're doing their experiments. And so having them wear wearable devices like this enables us to collect continuous data from the astronauts, although it does integrate an element of noise into the data. So if in the future, what we'd like to do is develop some sort of AI-trained doctor to help astronauts when they're in space to predict issues they may have early, what we need to do is first have data. And there's two types of data that we need. We need healthy data from the wearable device to get an indication of what does healthy look like when it comes from these astronauts. And we need symptomatic data. We need symptomatic data because we need to see what does a symptom look like, how can we find early markers of it. And the problem is right now, symptomatic data from these wearable devices doesn't exist. So that's the purpose of this project. The idea is to generate symptomatic wearable data that looks like it had come from these sensors, from these astronauts aboard the International Space Station. And a point to note is the reason we don't have this data is because currently all of the astronauts that are sent to space are really healthy. They've gone through many, many tests, for many, many years of process to go and be chosen to go to space. And so the few that are chosen, we know they don't have any heart conditions. So the few that we send to space currently are healthy. We know the data we're going to get back is healthy. But in the future, this might change if you think about potentially commercial travel and many more people visiting space. So before I dive into the specifics of our project and how we work to generate symptomatic data from the wearable device, I'll just quickly explain what an ECG signal looks like. And I'm sure this is basic for many of you in the audience, but it's helpful to kind of just talk through before we look at the output of the models. So on the left, we have what we consider just a healthy ECG signal. And the main thing to note is the P wave, the QRS wave, and the T wave. And on the right, you have a symptomatic signal. And the main thing that you see is that there's the lack of the P and the lack of the T wave. So we focused on this project specifically on atrial fibrillation because we were told by NASA that it's one of the conditions they think might occur in space that could have potentially gone undiagnosed. So what we'd like to do is generate symptomatic data, specifically for atrial fibrillation, were it to have been from an astronaut that was wearing that wearable device. So to build our models, there was two main types of data that we used. The first was clinical ECG data, and the second was wearable ECG data. So the clinical ECG data was from numerous open source data sets, specifically PhysioNet. So this clinical ECG data is symptomatic. It gives us an indication of what that specific symptom, atrial fibrillation, would look like were it someone in a hospital with a very clean signal, and we know that they have that symptom. The wearable ECG data gives us an indication of what asymptomatic or healthy data looks like when it were to be worn, were someone wearing that wearable suit. So what we can see from the wearable data is just an idea of what that noise looks like when it comes from the wearable device. What we can see from the clinical data is what that symptom looks like, and we're trying to incorporate both aspects of those into our model. This is the quick overview of sort of the two ideas, and this is valuable because this is how we sort of think about building our model. So what we say is that there's two main elements to any ECG signal. The first is the style of that signal, which we say is the wearable style that we're trying to incorporate. And the second is the content, and we're trying to integrate the symptomatic content into the signal. So I'll describe next the architecture that we use to build this model. So the first thing that we did is that we trained two discriminators. So the first was a style discriminator, and the second was a content discriminator. So what the style discriminator is trying to do is discriminate just a binary 1 or a 0. Is the given signal from a wearable or not? So we trained that first. And then we trained a content discriminator to say, is the given signal symptomatic or not? Does it contain that content of the symptom that we're looking to incorporate? We then built autoencoders for these two respective parts. The first takes in the wearable asymptomatic data and builds essentially machine-built features to represent that input signal. And we do the same for the clinical symptomatic. And what we care about specifically is this latent vector representation of those two signals. And that's a representation of what the signal looks like in this specific, as a latent vector. Those are then fused and fed into the generator, which essentially produces the output that we're focused on, interested in, which is the wearable symptomatic data. And what we hope would happen from this model is that it integrates elements of both. It integrates elements of the asymptomatic data from the wearable and also symptomatic content. The reality is once we create this signal, and this is an issue with many generative models, the signal that we're creating here doesn't currently exist. So how can we validate something that doesn't currently exist? And this is a question that we grappled with for a long time. And in short, I suppose our answer was that we compared it to different things that we know that do exist. And I'll talk a little bit about it here. So things that we know that do exist, what we do have as an output of our model is wearable symptomatic data. So what we can do is compare that to the wearable inputs that we know, wearable asymptomatic, and say, how similar is that? We can then compare it to the clinical symptomatic and say, how similar is it that? And those are two axes of data that we do have. And the last one, the symptomatic wearable, isn't something that we have and isn't something that we can actually validate on its own. We hope if we can validate the two other elements, that would give us an indication that the fusion of them is accurate, or at least an accurate representation. So what we have here on the top is the content that we're taking in as an input. These are 3 different time steps. And here on the y-axis is the style that we're looking to incorporate. That's again the style of the wearable. And what we see is that the machine learning algorithm is able to kind of fuse the two together. In the center is the actual output from the model, and we see that it has elements of kind of the noise from the wearable signal and also the content from the specific symptom, atrial fibrillation. So you can see the kind of the lack of the P wave and the T wave. This is very much a first step in the validation pipeline. We have a longer validation pipeline that will hopefully be out in a paper coming out in the next few months. What we can also do is visualize the different types of signal in embedding space. So what we have here is in red is our astroskin, which is a wearable asymptomatic. And we also have in black the clinical symptomatic data. And we can see as those are visualized in space, the blue, which is the output of the model, falls somewhere between them. And that gives us some indication that perhaps it is similar to both, but kind of in the middle of the representations of the two. So these are very much first steps in kind of looking at the outputs of the model and looking to validate them and look at our results. But I think that this work has a lot of potential as it fits into the kind of the broader picture of NASA and thinking about the future of astronaut health. So I think that's it for me. That this is kind of an overview of the project that we've worked on as we think about kind of the next steps in astronaut health. I think it's an exciting time to be working in space and thinking about space. So we hope that this can kind of be a step in prioritizing the health of all astronauts that go into space. I'm happy to answer any questions, and I'm looking for a job, so please hire me. Yeah. So the question was, did we visualize where clinical asymptomatic was? We did, and it's not here, but it's part of sort of our larger validation pipeline. What we'd expect for clinical asymptomatic is that it would incorporate some elements of potentially the wearable asymptomatic within it. I suppose it does, is kind of the answer. We don't have it in the slides here.